So we left off talking about three-way tables. I'm going to continue with that today. Our example to keep in mind is this Boy Scout example, where we have socioeconomic status being low, medium, or high. We have whether they're a Boy Scout, yes or no, yes or no, yes or no, and then whether they're delinquent. Yes or no. And we have some tables, 11, 43, 42, 169, 14, 104, 20, and 132, and 8, 196, 2, and 59. And what we're doing is looking at different models of possible models of this table. So it has three variables, maybe S, B, and D. And we have a hierarchy of different possible relationships that could exist between these. We last time considered and tested whether the model written as a hierarchical or log linear model in this sort of simplicial not complex notation where we write down the subsets that we allow to have interactions. So that's the independence model. And we tested that, and we found that it was not a good fit. And then we looked at the joint independence model, which I think was SB is related, but independent of D. And that was also a bad fit. And so we're going to continue considering models to try to find one that is a good fit. So the next one to look at is what's called marginal dependence, marginal independence. So in the second, we'll talk about conditional independence. This is the simple idea of form the marginal tables, like Nij plus, or in this case we might do N plus Jk. So here what we're doing is if the variables are ordered like S, B, D, we're saying we're ignoring S. So we're not controlling for S, we're summing over it. You get from that a table. In this case, it would be a 2x2 table, Boy Scout versus delinquent. And we want to find out if that implies whether that model fits. Okay? So this marginal independence model is a little bit harder to think about graphically. You know, if you think about an independence model as saying that I can represent some complicated table with two outcomes as just the outer product of two vectors. What this is saying is if I have a table with three variables and I sum over one of those variables that I don't care about, now it becomes a table with two things, and that table factors into two factors. So that's sort of a graphical representation of marginal independence. And if you think about what that means, something to note here is that I could have AB independent of C. If I have joint independence, that will end up implying that A is independent of C and B is independent of C. But the converse is not true. A independent of C, B independent of C does not imply that AB is independent of C. So in order to prove something, an implication does not exist, all you have to do is have a counterexample, a single counterexample. I'm not going to work through that now, but you can look in the online notes and there's a counterexample. So a particular table with three variables such that this holds and this holds, these two marginal independence relationships, so this is ignoring B and this is ignoring A, they hold but this relationship does not hold. Okay. There can sort of be a coincidence, if you will, that makes it when I sum over some other variable, I get marginal independence, but that doesn't hold in general. So that means you could have this type of relationship and another one when I sum over a different variable, but that doesn't imply that I have a factorization of the whole thing. Now, this brings up an interesting question. Okay, so that's the implication that does and doesn't hold. Among independence, conditional independence, statements. All right, so if I give you a bunch of variables and I tell you these are independent, like A is independent of Z given WY, and A is independent of B, and I just give you a bunch of these statements and I ask what other statements are true? What other statements can I conclude? So this question actually turns out to be surprisingly difficult. Shortly after people had formulated the idea of conditional independence, there was a proposal to try to axiomatize it, right? To try to write down some finite list of inference rules. These things hold, these statements hold, imply these statements hold. Right? This is an example of one of these inference rules. This holds implies that holds. Does there exist a finite list of rules? And under certain conditions, that can be done. But in the end, an author by the name of Milan-Studeni showed that no, there does not exist a finite list of these rules. So for probabilistic conditional independence, when I'm actually dealing with true probabilities, the list of such rules is infinite, and it's quite complicated to figure out what implications are created by a relationship. Under suitable conditions, though, it does get easy. And we'll see some of those conditions as we get to more complicated models. You can deduce all the, so in cases where the model has a certain structure, like it comes from a graph, and we assume that all the probabilities are strictly positive, for example. Under those conditions, then these implications are easier to deal with. But in general, there's no finite list. I should say that the proposed finite list was something called a semi-graphoid. And we'll talk a little bit about graphoids and things like that, just as needed. So the semi-graphoid axioms almost do it, but don't quite do it. Okay. So let me see, do I have the calculation for this? Somehow I didn't write it down, but if you do this test on the Boy Scout example, it doesn't fit either. So I do a Pearson chi-squared is big, appropriate degrees of freedom, and P is close to 0. That tells me that it's not a good fit for the model. In other words, I take the whole null hypothesis is always, it lies on the model. The alternative hypothesis, it doesn't lie on the model, where it's saturated. I compare those two using a Pearson test, and I would get a low p-value, which means this model is also a poor fit. So let's move on to the next type of model, which is a conditional independence model. And in my opinion, the conditional dependence models are probably the most important class of models because they're easy to understand what they do. They have nice graphical representations often, and they result in much more tractable inference problems. So when you have a lot of variables and you have this conditional independent structure among them, it's a lot easier to solve the problem of like what the maximum likelihood estimate is. Whereas for an arbitrary model, that problem can be quite difficult. Okay, so I've been giving you kind of a list of different representations when possible, so let me give you some of these for conditional independence. So the first is this graphical model notation. And today we'll get a little bit into what more carefully discuss what this means as soon as I show you something where it can't be represented by graphical model. But approximately, it's that I write down my variables, and then I draw an edge between them when they're related. More accurately, I should say that they don't have an edge if they're conditionally independent of each other, given the ones in between. So A and C don't have an edge. So really what this says is that A and C are conditionally independent, given the part of the graph that separates them, which here is just B. Okay. So I could say it's conditional independence statement is just A is independent of C given B. And it can be read off from this graph. You can see that it's very close to the idea of sort of separation in the graph, which is why this kind of idea is connected to the idea of conditional independence. I have some variables that get between A and C, and that is a graphical way to represent that they explain all of the correlation between A and C. I have this tensor notation. For this, I would write something like I'd have a node for A, one for B, and one for C. I would explicitly write these parameters that connect them. I'm going to name this parameter theta AB, or a matrix of parameters, theta BC. And then I put some wires to show what things are visible to the viewer. So this is just kind of an expanded version of this that explains more what's going on. You can think about it that way. The simplicial or log linear notation for a model, this particular conditional independence model would be AB comma BC. That is, we're zooming in, or we're most interested in the factors of the interaction between variable A and variable B and variable C. Because of the nature of these things, I'm also allowed anything that's contained in this. So A, B, and C by themselves, like I have a parameter that modifies them. And these maximal subsets that I list here in this notation correspond to the boxes here. And they correspond, in this particular graph, to the edges. In general, they're going to correspond to something called a click in the graph. But in this graph, it corresponds to these edges. Okay. So what we're sort of saying in words is that, well, if I know the state of B, A and C can be taken to be independent. Another way of thinking about it is that all the interaction factors through these two boxes, or through the relationship between A and B and the relationship between B and C. So let's explicitly write down a factorization property. And a couple of different ways of thinking about that. So I could say P of AC given B equals P A given B, P C given B. So this is conditional independence. And let me expand this statement and explain why I'm writing it this way. So this is another way of saying probability that big A, the random variable, equals little a, the outcome of the variable, big C equals little c, given that big B, the variable, is equal to the state, factors as probability big A is equal to little a, given big B, big C rather, is, no, I'm not conditioning on B, right? Big B is equal to little b times the probability that big A is big C is equal to little c, given B equals B. Okay, so this is a little bit cumbersome notation. This notation here is just an abbreviation of this. Now, why don't I just use the IJK stuff that we've been doing? Because if I write something like Pi given ij given k, you know what I mean. But if I write P10 given 1, well, it's not which 1 and 0 is this, right? So is this C or is this B or is this A? You can't tell from this notation. Okay. So you have to be careful with that, right? So if I want to write that out, I might have to say something like I equals 1 k equals 0 given j equals 1. Okay. But that's just the reason that I write these letters here, because otherwise this makes clear which things correspond to which variables. Okay. Okay, so this is a factorization property, but it's different than the other ones in that it's expressed in terms of conditional probabilities. And it doesn't tell me what the actual joint distribution is. Right? So I still don't have the full joint distribution. To obtain the full joint distribution, what I should now do is use Bayes' rule on this. Right? So Bayes' rule tells me that P of A given B is P of AB PB. Right? And so if I reverse that, I move this up there, it says that to get from this a full joint, I just have to multiply by whatever I've conditioned on. Right? So this tells me that probability of ABC equals probability of AC given B times probability of B. And now these things are things that I can estimate or expand the expression of. Right? So then using the fact that probability of AC given B is under this assumption A given B, C given B, I can write this is probability of A given B, probability of C given B, probability of B. So you can think of it as kind of like a tree, right? I start some root, and then I multiply it by a bunch of conditionals. And that's the factorization of ABC in terms of this conditional independence statement. And then I would need to estimate these from the data, but I can do that just by looking at ratios, right, in the usual way. Ratios of counts. So I've also offered, when I could, something in terms of the defining equations for the model or the effects that we're presuming to be really the non-effects, right? What effects do we think are zero? Or another way of saying that is what equations do we think hold among the probabilities in the model? And what we're saying here is the conditional odds ratios are all 1. Right? Some things like theta AC, or the appropriate conditional odds ratios, let's say all. So like theta AC given B is an odds ratio that corresponds to the table of variables A and C fixing the state of B. So if there are 5 states that B can take, there are 5 of these tables, and we're saying that all of these tables are equal to 1. And you can expand that and get an equation in terms of these conditional probabilities. You could expand that further and get an equation in terms of these, but it's going to be a more complex equation. Okay, it's not as simple as the other ones. Another way of saying that is that if I take different states, probability of AC given B, probability where A prime and C prime are just other states that the variables A and C can take, given B, divided by probability of A prime C given B, probability of A C prime given B equals 1. And I can multiply this out, and I could write these things out, and I would get a bunch of equations. And to test for conditional independence, to get a hypothesis test, I make estimates of everything, and I compare them to, I test whether these things are actually true, whether these odds ratios are actually 0. Okay. So I want to say a few words about interpreting this, interpreting conditional independence. Hopefully you have some intuition already from what I've said, but before I give an example, let's say a few more words. So some phrases: given the state of B, A and C are independent. Just in the usual probabilistic notion of independence. A and C may be, not necessarily are, but they may be associated that this is explained away by B. Once I understand B, the association disappears. Right? It's like it's a classic situation where you look at data, you find a spurious correlation, or you find a correlation, it might be very strong, but as soon as you add in some latent variable that affects, say, the mix of things, this correlation goes away. Right? Just like the example with the dogs and some examples we'll see from the notes, like admissions. We might say there's something like controlling for B, A and C are unrelated. And you could think about it as kind of a weak version of the Simpson's paradox. So Simpson's paradox says the marginal and conditional association measured by odds ratios or measured by whatever can be reversed. Right? I can have a 2 by 2 by 2 table in which the marginal relationship, when I sum out by one of the variables, I sum out by B, the marginal relationship can go in one direction. When I condition on B, the relationship can go in the opposite direction. Right? So conditional independence is kind of a weaker version of this. This says let's say marginal theta can be non-zero or non-1, and the conditional odds ratio could be 1. That can happen. Right? So this says not that it goes in a different direction, but that the relationship is destroyed when we move to conditional. And sometimes you could think of it as a special case of this situation, where they're just different. And of course, we don't mean literally 1, we mean not significantly different from 1. And so this is such a common situation, both Simpson's paradox and a lurking conditional independence, that pretty much any time you read a study that says this is associated to this, you should always be worrying, is there some variable that we didn't account for that would make the relationship disappear or reverse direction? It's like a classic mistake. On the other hand, if you're trying to lie with statistics, then pick a variable to sum over, that makes that go away. Right? And that will help you to make your case, whatever your case is. Okay, so to do inference for this, it's similar to what we would do for any of the others. That is, we use factorization, use this factorization property and MLEs to compute cell probabilities, Pijk, and multiply by the grand total. And then we get Eijk's. So for example, for this A independent of C given B, we would use PABC equals PA given B, PC given B, PB, and we'd get an estimator, PABC. So this is given the null, which in this case is conditional independence, or more specifically, A is independent of C given B. So the estimate given the null, so this is akin to our estimate for the independence table, right? It's not the saturated model, it's the smaller model. Should just be, I just plug in A, probability of A B hat, probability of C given B hat, probability of B hat. And these I can compute from the counts as N AB plus N plus B plus. Right, that's the first one, probability of A given B. It's just the count of A given B divided by the total count of B. N plus BC over N plus B plus times N plus B plus divided by N plus plus plus. Right, so these are just these obvious estimates for these conditionals. And kind of part of the magic of this particular model is that these estimates are so easy to obtain. Right? We'll see in a moment a model that's slightly different than this. It doesn't look much more complicated than this, but where instead of getting this nice closed form formula for the estimates, you have to run an optimization algorithm in order to get the estimates. So a lot of the appeal of conditional independence is just to be able to do this kind of, or conditional independence models is to be able to do this very simple estimation. So once we have these, then we can do our usual tricks. A G squared or a deviance statistic or a Pearson statistic. And what we're doing, of course, implicitly here is we have kind of a saturated model, ABC. All relationships are allowed. And I have this restricted model, ABC. And I'm testing to see whether, how if this model is more accurate or that model is more accurate, and the degrees of freedom or the degrees of freedom of this minus the degrees of freedom of that. So let's talk about the degrees of freedom for a moment. So at this point, I want to give you a warning, which is that sometimes it's tempting to sort of look through these models and be like, OK, this model has this degrees of freedom in terms. Don't do that, because you'll very easily make a mistake in terms of what the degrees of freedom should be. Just compute the degrees of freedom here, compute the degrees of freedom here, and subtract. Okay? It takes one extra step, but you won't get the wrong thing. So for example, in this case, the degrees of freedom depends on which of the three conditional independence models we're considering. Right? So for example, I could look at A independent of C given B, and suppose this has I states, this has J, and this has K. Then our degrees of freedom for the model, not for the test, but for the model, are J minus 1. So that's just for the vector PB. Right? I have a probability of each marginal state of the B variable minus 1, because they all have to sum to 1. And then I have conditional tables for each of these other guys, A given B and C given B. So I have J possible inputs, possible states of B, and the outputs of this table, or the rows of this table, they're I minus 1. So that would be the probability of A given B. Right. This parameter, if you think of it as a parameter, has this many degrees of freedom. And for the other one, for C, it would be K minus 1. So that's probability of C given B. And if I change my independence model, A independent of B given C, then I get, of course, a different formula for the model degrees of freedom, K minus 1 plus K I minus 1 plus K J minus 1. So this is PC, because that's the conditioned upon vector. This is PA given C, and this is PB given C. And if I do the other model, probability, or B is independent of C given A, then I get I minus 1 states in the vector of probabilities, marginal probabilities for A, and I add that to I times J minus 1 plus I times K minus 1 for probability of B given A and probability of C given A, respectively. Okay, so you should think about each of those things as tables. And then, so the test degree of freedom, of course, is this one, which is I times J times K minus 1, minus whichever one of these you're testing. And if I, J, K are not equal, they'll all be different numbers. Right? So the test degrees of freedom is I, J, K minus 1 minus whichever one of these. Let's say we're doing these degrees of freedom B independent of C given A. If we're testing a B independent of C given A model, then you do a little algebra, and you get, in this case, I, J minus 1, K minus 1. So that's the formula. So in the notes or something, you'll see this formula. But I recommend not memorizing those. Instead, just calculate it each time so that and subtract. People very often get confused about, are we talking about the model degrees of freedom or the test degrees of freedom? So just always figure out the model degrees of freedom and subtract. And also that's important later when we want to test, instead of testing everything against the saturated model, we'll sometimes test nested models against each other. And in that case, there's no other choice but to do that. Right? Okay, so that gives us a full procedure for testing goodness of fit of the conditional independence model. Because now we can just sort of go to our usual multinomial trick. We have a model estimated probability for every cell. We have a model estimated contents, cell contents for each cell, and we have an observed contents. And so we just compute Pijk hat and Eijk hat, or not hat, that's just what we see in the table. And then we get our Pearson or deviance statistic, or both, usually both, and compare to chi-squared with a nu degrees of freedom, where nu is degrees of freedom saturated minus degrees of freedom model, whatever that is. Okay. And then we get our hypothesis test. So there's this other test called the Cochran-Mantel-Hansel test that we should mention, which is kind of a specific version of this that tries to get the degrees of freedom down. There are a lot of these because we'll have this nice general framework, but also people have cared for various reasons about asking specific questions, maybe because they're not thinking about it in terms of a big framework. Or it was before that we thought about things that way. And so there's a lot of specific tests, and this is one of them. This is for 2 by 2 by k table. And the idea is that in such a table, right, each level of the table, each k level looks like n11k, n12k, and 21k, and 22k. And we can compute something simpler by just looking at the first cell, which tells us a lot about the table, or all about the table, depending on your sampling assumption. And say that under the hypothesis, the expected value for n11k should just be the conditional independence assumption, and 1 plus k and plus 1k. So that's taking the marginals, fixing k and taking the marginals that you would get from independence divided by n plus plus k. Really, there's 2 n plus plus k's, and then there's 1 on top, and they cancel. That's why there's only 1 down there. So there's 2 to get the p, and then I multiply by 1 to get the e. And if you do that and sum all the deviations from that expectation, you get a test that only has 1 degree of freedom. Which is sort of a little bit simpler, I guess. Which is m squared. I'm going to write CMH down here just to distinguish it from our other m squared. So this is the sum over all of the levels of the variable we're conditioning on, and the actual observation in that first cell of each of the k tables minus that expected value for that table, that cell. And I want to square that and divide it by the sum of the variances of these n11k's, where the variance of these n11k's is computed to be n1 plus k, and 2 plus k, and plus 1k, and plus 2k over n squared plus plus k, and plus plus k minus 1. And if you do that, then one can show that under suitable assumptions and for large samples, this is approximately chi-squared with 1 degree of freedom. Under the null, And what's the null here? Of course, it's the conditional independence relationship that we posited holds. So the point of that is kind of to find a one parameter thing, right? The other one will have the degree of freedom that will be the difference between the saturated and the.
Do you square it first and then sum it, or do you sum it first and then square?
I think you sum it first and then square. Because otherwise, yeah, I think so. And there's a warning, which is that to use this, this test doesn't work unless all the odds ratios go in the same direction. So all the odds ratios should either be greater than 1 or less than 1. Practically, what does that mean? If I ask you on a question, compute the Cochran-Mantel-Hansel test of conditional independence, part of your answer should be checking that all the odds ratios are in the same direction, because otherwise the statistic doesn't behave correctly. Okay, so let's look at the Boy Scout example and just say what happens. So for the mutual independence, or full independence SBD model, we got a Pearson chi-squared of 218 or so with 7 degrees of freedom. And so P was pretty much 0. For joint independence, specifically that we have scouting and SES are related, but jointly independent of delinquency, we would get a Pearson statistic of about 33, and the degrees of freedom was 5. And P is not quite as small, but still small. So those are both pretty terrible fits. We could try this ignoring or marginal independence model, which would look like yes, no, scouting, and delinquency. And just test that for independence, which you can almost do in your head, but this one's going to be about 7.5 with 1 degree of freedom, and the P is 0.006, and so we can reject that one too. And so this is the, if you were trying to encourage people to send their children to Boy Scouts, this is the table you would use because the relationship is pretty strong. The odds ratio of comparing scouting and delinquency and just ignoring socioeconomic status is 0.54, which tells us that the Boy Scout manual might say, your kids are only half as likely to be delinquent if they go on the odds ratio scale. Right? If you're trying to sell this product. But as whenever someone reports a statistic like that, you should be skeptical that there's some variable that they haven't considered, controlling for which the effect would go away. And of course, that's the story here. I wouldn't be using it as an example. And to show that, what we should do now is to test for conditional independence. So we want to do the test, or we want to check for the null hypothesis. B is independent of D given S, so that's his socioeconomic status, this is delinquency, and this is Boy Scout. And we can use either of the two procedures we talked about. So you could take a Pearson or G-squared test, adding up what we would get from all the conditionals. And this will give us 0.016, which are not 0.16, 0.16. Which is very small. And that's a p of 0.984. Okay, so that tells us, wow, okay, we went from absolutely terrible fits to a really, really good fit as soon as we did this conditional independence model. And so what our conclusion would be something like accounting or controlling for socioeconomic status, scouting has no effect. And we'll talk a little bit later in the class. So of course, there's this hierarchy about these models. And you could be a little bit prickly and say, well, great, it fits now, but is 0.984 or is 0.16 significantly different from that, right? That's like another test we could do. So we'll talk about later how to do that test. But for the purposes of now, we just see a dramatic difference in fit, something it rejects, and something that can be accepted. And we can think about the cause of this. So the cause, just like Simpson's paradox, we can think about the cause of this thing by looking at the tables. So there's an apparent relationship. And often you can see it from the marginals. So I look at the marginal tables scouting, yes or no, and socioeconomic status, low, medium, high. And this table will be 54, 211, 118, 152, 204, 61. And the other table would be delinquency, yes or no, versus socioeconomic status. And this table will be 53, 212. So I'm just summing over the other variable, 34, 236, 10, and 255. And what you're supposed to see here is that we have a strong positive relationship here, a strong negative relationship there, right? And there's no additional, these two relationships kind of link together to cause the effect that we see here. But once we account for this other variable, there's nothing left, right? We could have a situation where these were linked and there was a further interaction between the two, and that it went, that there was still a relationship. That would be like an interaction term in a regression, like a term in the next order. And of course, the CMH statistic here, because everything is all the odds ratios in the right direction, would also work to find that this was a good fit. So the last model I want to discuss today is the model of what's called homogeneous association. And this will highlight a couple of problems with the way we've been thinking about these dependence structures. Kind of opens a can of worms that we have to deal with. But first, let's say what the model is supposing. So what it claims is that the conditional relationship between a pair of variables, any pair of variables, given the third, so we have three variables still, is the same at all levels of the third. So there's a special case which is right, the relationship is 1 at all levels. That's what we saw in conditional independence. Right. So this is letting that be non-1, but be fixed. Okay, so let's write down its various representations. So here, with this type of model, we run to the end of things that have graphical model representations. So this is not representable. But there's sort of good news, which is that there's a slightly expanded version of the graphical model notation for which it is representable. This is called a factor graph. So if I write A, B, C, I put a little box at each of these. So the factor graph representation looks like that. And this tensor representation is almost the same as the factor graph representation. It's just that it also has these extra wires that keep track of what things are visible to the person looking at the experiment. So these are almost the same. It has a simplicial complex or log linear representation, which is all pairs, AB, AC, BC. There are no independent statements, although it's not a saturated model. So the independence story doesn't really describe what's going on here accurately. And it has a factorization, which is nice, but not as nice as the conditional probability one. So the factorization looks like the probability of ABC is equal to the product of some parameters, the value of which depends only on A and B, multiplied by one whose value depends only on A and C, multiplied by another that depends only on B and C. And then I have to correct by dividing by the sum over all possible ABC of this number, AB, AC, BC. Usually, often this is sort of taken out, but you can think about it's proportional to the product of these three quantities that live on these factors. There. Okay. So what is a factor graph? And what's going on here? Why does the graphical model idea no longer work? So a graphical model, so now I have to go beyond 3 just to sort of explain what's going on. So if I drew the graphical model, let's say this one, and let's do a couple. Here's 2 graphical models. They have factor graphs, or the factor graph is basically just a picture of the log linear notation. So it tells you what are the maximal parts of the graph. And what they are is I take the cliques of the graph. A clique is a completely connected subgraph. So in here, there's 2 cliques, right? So I could do it like this. In here, there's a clique for this, and this is a clique too. It's a completely connected subgraph, but it's just not very big. So this one would look like I'd have these 3 connected, and then I'd have another one over here. Okay, so for a small thing like a triangle, the graphical model can only represent one thing. Right? This only can give you the factor graph that looks like this, because it's a clique. It's completely connected. So in order to get the homogeneous association model, we need to allow for the idea that all 2-way interactions are permitted, but there are no 3-way interactions. And we can't even represent that if we're forced to use this notation. We can represent it as this notation. This is not the same as this guy. Again, this factor graph is really just the same as this log linear notation that you'll see that the computer understands. It's just a way of picturing which of these subsets do we put in our factorization. which of these subsets do we have to estimate in order to estimate our model? How do we think the dependent structure breaks up? So in this case, it's not true, by the way, that I can replace these with probabilities. It's not true that the ABC this is not equal to P AB, P BC, P AC. Right? I could get marginal distributions. I could sum over the third one, and I multiply them together, but I would not get the answer from this model under homogeneous association. Right? That's like what we would hope would work out, but it doesn't work. Okay, so don't. Instead, we need to use this parameterization, and in order to fit it, you have to solve an optimization problem. To find P ABC, now that we're out of the realm of conditional probabilities, we're out of the realm of things that can be described by conditional tables and marginal tables, we have to just optimization. What is the optimization? It's this. It's from P hat ABC, which is equal to this thing, AB, BC, CB over Z. I'm just going to Z for that sum. So I do that. I form a likelihood function based on my P hat, this P hat, and my data. And then I have to maximize this likelihood function of the inputs, which I could think of as this is a function of theta AB, theta BC, and theta CB, and the data, right? Because from these three parameters, I construct probabilities. From the probabilities and the data, I construct a likelihood. I want to now maximize this as I let these parameters vary. And so this is the first example for which there's no closed form. So there's no simple formula I can write down for this solution. Instead, what happens is there are various computer routines that you can use to solve that optimization problem. For a small example, like a 2 by 3 by 3 table, it doesn't much matter what technique you use. For bigger examples, the efficiency of different techniques will be quite different. Popular techniques include something called iterative proportional fitting. This was the first technique that was used to solve these things. This kind of multiplicatively adjusts each of these until we get closer to the goal. There's sort of general purpose ones like Newton, Raphson, and there's something called, for big problems, you want to use some other, this is called limited memory BFGS, which is just like an optimization that constructs a simplified version of the Hessian matrix of these things. So anyway, under the covers, for this you need to punt to the software for some optimization routine or write your own optimization routine. Once you do that, it will run some algorithm that's hopefully appropriate for your situation to find good values of these parameters and find a good estimate P. Okay. So this has a statistic. The statistic is called Breslow day test statistic for homogeneous association. And it's basically just a Pearson statistic, observed minus expected. It's just that now our expected is not calculated by hand. It has to be calculated by this optimization routine divided by expected. And this will have degrees of freedom k minus 1 under the null hypothesis that homogeneous association is true. So now let's organize all of these models into the hierarchy. So we have at the bottom we have an independence model, ABC. And since I'm telling you that the factor graph or the hierarchical log linear model simplicial complex notation is sort of most efficient, I'm going to use that notation. So we have at the bottom this kind of fully independent model. Then we have all of the ways that two can be independent of the other. And then we have our conditional independence models. So maybe I should write these. This is like A, B, C. This is A, C. Or let's skip it like that. A, C, and B. This is A and B, C. So now I'm writing the graphical models. Or if we want to let's make them factor graphs. We just put little boxes in there so that we can represent everything. ABC is just this one where they're all completely separate. ABC. Then I can do the conditional independence models. A, B, C. So this is AB and BC. I can do ACB. I'm just changing the order now. So AC, CB. And I can do the last one, which is, what am I missing? AC. What's the last one? What is it? AB, AC? Yeah. Okay. So now everything is centered on A. Put A in the middle, put B over here, put C over here. So those are the conditional independence models. Then I have the homogeneous association model, A, B, C, which right now in the online notes says has no graphical representation, but now you know that it does have a graphical representation. You just have to go to factor graphs. And this is AB, AC, BC. And then at the very top, we have the saturated model. Oops. A, B, C. A, B, C. And in this notation, again, you should think about these as always saying these are the maximal subsets in the model that we're interested in. You should think about this as being a way of writing this and all smaller things. So this contains also A, B, C. Right, so really this is A, B, C, and AB. It has 4 subsets in it. And this is A, B, C, AC. And this one is A, B, C, BC. And this has A, B, C, AB, BC. A, B, C, AC, CB. And A, B, C, AB, AC, and this one is everything so far, A, B, C, AB, AC, BC, and this is everything, every possible subset, ABC, AB, BC, AC, ABC, right? And so this is why they're called hierarchical models. Each of these models below is contained in, not each one above, but this one is contained in all of these. And then you have to be careful. So this one is contained in that one and in that one. This one is contained in this one and in this one. This one is contained in this one and in this one. So it's kind of like a cube, right? It's a cube picture of a cube in a very strange way. And then you can just take a picture, okay? I could do the next level up here. Did I not draw the, oh, no, that's it, okay. So all of these are contained in this, right? And then this is contained in that. So that's the full hierarchy of possible models of this type. of the log linear type, or of this sort of what's called hierarchical models. On 3 variables. And every arrow there has its own test. And the arrows are transitive. So mostly what we've been doing is testing yes or no for each one. Right? We've tested this versus that, this versus that, this versus that. And you can see why that will give a similar answer. Right? If I test this versus that and I test this versus that, I can figure out what this test was. But it also makes sense to test any inclusion. The ones that are not included in each other, maybe we have to do a little bit more thinking in order to decide what a reasonable way to test this versus that is. I mean, we can just compare their goodness of fit statistics, but we have to, if we really want to compare, right, if you get a goodness of fit statistic for this, you get a goodness of fit statistic for this, you say which one fits better, you can answer that question. But if you say which one is the fit of this significantly better than that, we don't really know how to answer that yet. Right? Okay, so this theme here is, as you're probably beginning to see, this problem, this sort of problem is called model selection. Once I pick a model, I know how to check goodness of fit, I know how to compute maximum likelihood estimates and do inferences and create confidence intervals and all of that. But the question is, what is a method for choosing the best model is a very difficult and subtle problem. Of course, one answer I could take is always choose this model. This model will always fit perfectly, but it will tell me nothing about the data. Right? So I want to choose this sort of, the rough way of saying it is I want to choose the simplest possible model that's a good fit. But this is with only 3 variables. If you had 100 variables, you can imagine that this would take a little bit longer to draw this picture, right? And so for any reasonable, so you can think about, what we really want is some way of assigning a score to each of these models, right? Which balances how well they fit with how complex they are. Right? So this one doesn't get the best score. It always fits perfectly, but it has some kind of penalty for its complexity. And let me say that for any reasonable score, this problem of model selection is what's called an NP-hard problem. So I don't know if you know what that is, but it means, in a formal sense, that it's a difficult problem to solve. Right? It's something that as the number of variables increases, there's no way that the computer will be able to solve that problem, let alone the person, in the worst case at least. And so what we end up having to do is create various heuristic methods for making a decision as to which model to use. It would take too long to test them all. It would take too long to search them in any systematic way that was guaranteed to find the right answer. So we have to come up with some strategies. And as we move on, of course, we'll talk a little bit about those kind of strategies. So it's both NP hard and it's sort of hard for people too. And so what you'll have to do is to look at the data, stick to testing things that make sense to you, right? So like the Boykout example, we didn't take every branch in this diagram. We just looked at a few things that could make sense, sort of like one path, and stopped. So we took one path, like maybe this path, and we stopped here because it fit. Right? So that's one strategy you can use. You can say, I pick one path that reflects my understanding of the data, and I stop at the point where it gets a good fit. That's a pretty good strategy. Or there's a couple paths that you want to consider because a couple of different paths make sense for the scientific question that you're looking at.